Welcome everybody back to another lesson. Today we're going to be talking about concavity and what that means and how we can use that to help us curve sketch. Okay, so the theme has been curve sketching for the past week or so. Before that though, if you wouldn't mind, could you please hit the like button on this video? It helps out the channel greatly. I'm going to put up a picture of a sad cat right here. Hopefully I can find one. And if you press the like button, the sad cat will disappear and be replaced with a happy cat. So please press the like button. It only takes 2 seconds. Okay, here's your happy cat. Okay, so in all seriousness, hopefully today the audio quality is better. I tried adjusting the mic, but the mic is, I think it's just not a good mic, but I've amplified the sounds in iMovie, and hopefully you can hear a little bit better. Okay, so today the objective is to be able to describe where a function is concave up and concave down, and we're going to be using something called the second derivative to do that. So first we have to define what these words mean, concave up, concave down, and also how they're connected or related to second derivatives. Okay, so let's get into it. So please take as much time as you need. I go through these videos, the concepts a little bit quickly, but you're going to need a lot of extra time to write down things into your notes. Please do. That makes it easier to learn the math, and also makes it so that you have a place to refer back to in your notes. Okay, so I want us to consider two functions. The first on the left here, y equals x squared, and then on the right here, y equals negative x squared. So let's first take a look at y equals x squared. I've drawn 3 tangents here. One's in purple, one's in green, and then another one in blue. And these 3 tangents here just represent the slopes of the curve at x equals -1, at x equals 0, x equals +1. And what I want us to do first is just find the slopes of the curve. So to do that, we could take the derivative, because the derivative represents the slope of the curve at some x value, also represents the instantaneous rate of change of y near some x value. If we find the derivative, we get 2x. And if we plug in -1, for example, so say I wanted the slope of the purple curve, just plug in -1 into here and I get -2. And that's fine. And then if I plug in x equals 0, I get the slope of the green curve here. So the slope of the green curve will be 0. And then if I plug in x equals 1, I get the slope here. So that's going to be m equals 2. Now, that's fine, and that's what the first derivative represents graphically. And today I'm going to be using that word. I'm going to be using the word first derivative. So from today onward, I'm not going to be saying just derivative. If I'm talking about the normal derivative we've been talking about so far, I'll use the word first derivative. Okay, so what does the first derivative give us? Well, graphically it gives us the slope of the curve, or the slope of the tangent to the curve at some x value of our choosing. Now today what we're going to be doing is we're going to be going a step further, and this is where things get a little bit strange and a little bit like the movie Inception if you've watched it. But if the first derivative represents the instantaneous rate of change of the y values, what we're going to do is find the second derivative, which will represent the instantaneous rate of change of the instantaneous rate of change. So in other words, if the first derivative graphically gives you the slopes of the curve, so it gives you these slopes, the second derivative gives you a measure for how fast those slopes change, or it gives you a measure for how the slopes are changing. Okay, so let's do that. Second derivative you can find actually in the same way as taking the first derivative. Normally with the first derivative, you start with the original function, you take the first derivative, you end up with your derivative. Just take the derivative of the first derivative to get the second derivative. Or in other words, take the derivative of the original function here twice. So if we take the derivative of the original function twice, we just get 2. And we call this number here the second derivative, because we've done the operation of taking a derivative twice. That's not right. Derivative. Okay. So, couple things. First thing you might notice is that the second derivative just is a constant. It's just a number. It's the number 2. It's always positive. And that tells us something about how the slopes are changing, how the slopes of the curve are changing. I'm going to write down the slopes of the curve here in a different color, maybe with, maybe we'll use blue. So at x equals -1, okay, so at x equals -1, the slope is -2. At x equals 0, the slope is 0. At x equals 1, the slope is 2. And at x equals 2, if you wanted to evaluate the first derivative at 2, you would get a slope of 4, and then 6, and then so on. And you can kind of see that there's a pattern. And the pattern is that the rate of change of the slope values happens to be a constant. The slopes themselves, the rate of change of the slopes is a constant. So the slopes are increasing at a constant rate. Meaning for each increase in x, I increase the slopes by two points, okay, and so on. We keep doing that. So that's kind of interesting. It's interesting that parabolas have slopes that increase at constant rates because things grow and shrink at different rates. So, for example, a cubic's not going to have constant increases in slope. The increases are going to grow linearly, actually. And so the rate of growth is very different. But this is what I want you to think about. Okay, and this is kind of the main idea. The idea being, imagine if you were here on the curve, the slope would be large and negative. And then, it turns into maybe a smaller negative value. And then as you get to 0, the slopes are 0. And then you go to 1 and the slopes become positive. As you move away from 0, the slopes become positive. And then they just keep becoming more and more positive. So overall, you're going from a large negative slope to a 0 slope back up to a large positive slope. And so throughout that process, the slopes are increasing. Okay. So here, the key idea, and this is the key idea, for this curve, the slopes are always increasing. And we have a word for shapes that do this, or curves that do this. Curves where the slopes are always increasing are called curves that are concave up. And the way I like to represent that is with some arrows, okay? I know there's a lot already on this diagram, so I use these arrows here, and these arrows signify just that the curve is concave up, okay? Or that this is a concave up curve. You can see that the curve almost faces in the upward direction. And so we have a curve that is concave up. Its slopes are always increasing. By the way, the slopes don't have to increase at a constant rate. It's just a special case here because we're dealing with a parabola. The slopes just need to be increasing if the curve is concave up. And you can see the curve faces upwards. The trick that I like to use to remember if a curve is concave up, if you imagine taking some water and pouring some water, maybe into the parabola, on top of the parabola, I should say, the water would kind of sit inside this bowl shape. So anything that can hold water, if you pour it from the top, we can say that that's a concave up shape. Okay, so let's do the curve on the right here. F of x equals to -x squared. So we kind of do the same process. Maybe we find the first derivative. We notice it's -2x. You find the derivative of the derivative, and that's -2. And again, we notice something. We notice that this derivative here is also constant. So this is a constant second derivative, but in this case, it happens to be a negative value. And what does that tell us? Well, that tells us that the rate of change of the slopes is negative, and it's always negative. And you can confirm that with a few points, but the idea being here, overall, if you imagine, and there are many infinite collections of tangents along this curve. If you imagine maybe letting x go from -infinity all the way up until +infinity, the slopes here, the slopes are going to go from +infinity, to a small positive, to 0, to a small negative, to a large negative, and so on. So here, the slopes are going from a large positive value down to 0, and then to a large negative value. And so the slopes are decreasing. And that's what it means. That's what it means to have a second derivative that's always negative. Okay, so here, the slopes are decreasing. Now, this concept is kind of difficult and a little bit abstract. So it's okay if it takes you a while to get it. It's very hard to visualize slope. It's easy to visualize y values and like y values increasing and decreasing. But as soon as you talk about like, the rate of change of the slopes, it kind of gets very difficult to visualize. So just be patient with yourselves as you're trying to kind of wrap your head around this. So if the slopes are always decreasing, we call that curve a concave down curve. And I'll represent that with arrows kind of pointing downwards. The curve is almost facing downward, or it kind of flexes away from the x-axis in the downward direction. And here, if you imagine you had some water and you tried to pour some water on top of the curve, all the water would kind of slide and fall, and it wouldn't be able to hold the water. So like this shape might be able to hold the water if you pour the water from above. Whereas this shape, all the water would just kind of fall off. So that's what it means to, what the second derivative is, and that's what concave up and concave down mean. Hopefully that is a good introduction. Now I want to go over 4 shapes that you need to kind of be comfortable describing the concavity of. Before that, please just pause the video, jot down anything you need to.